same problem is we can use the Gibbs of formation of the products minus the Gibbs of formation of the reactants, and we'll get the difference between the two to get the Gibbs of the reaction. And these are all under standard conditions, so oops. Second way you can solve for Gibbs of reaction is to take the Gibbs of formation of the products and subtract the Gibbs of formation of the reactants, just like we did with the enthalpies of formation. And the difference between the two is the Gibbs of the reaction. And these are all standard conditions, so I'll go ahead and do that. So what I'm doing is I'm saying I have, for the change of Gibbs of reaction, under standard conditions, I can see the Gibbs of formation of the 2 moles of water is going to be 2 times that's negative 237.129 kilojoules per mole. And from that, I would be subtracting the Gibbs of the reactants. But notice my reactants are actually elements, and they're elements under in their standard state. And this is standard, so it's under standard conditions, which means 0, because it takes no energy and it releases no energy to turn a mole of hydrogen gas into a mole of hydrogen gas. It already was that. Okay, so I just end up with the same answer we had on the last one, negative 474.25 kilojoules per mole. So, what we just did, Gibbs of the reaction. We just saw a second way to solve the same problem. The Gibbs of reaction under standard conditions for this guy, using this equation and getting the same answer that we got using the other equation. And you can also see that the other one was pretty easy. Had we recognized immediately that this was a formation reaction, that this was making it's twice a formation reaction. We're making 2 moles of a compound from elements under their standard conditions. We could have just said, hey, what's the Gibbs of formation of liquid water? And double it, which is basically what we did on this step.